In this course, we have seen evidences and concerns of too much CO2 in the environment, which leads to global warming and irreversible effects on climate change. So, we need to cut our emissions by 50% over the next 20 years. Or we need to do carbon capture and sequestration to cut our CO2 emissions.
Carbon capture and sequestration is the process of capturing carbon dioxide from power plants and transporting it so it does not enter the atmosphere. CCS serves as an avenue to subsidize fossil fuel emissions that directly impact the issue of global warming. And as you can see, current storage is primarily underground geological formations. Theoretically, CCS has the potential of reducing CO2 emissions by up to 90%. CCS is not limited to a single method, and a myriad of technologies currently exist. The dominant method is using MEA as a solvent industrially. However, problems exist with this prevalent method. Let's listen to what Professor Reimer has to say about MEA technology.
There are a couple of serious problems, the most serious of which is the fact that it uses a great deal of energy to regenerate the MEA, that is to remove the CO2 from the MEA. So there's a big energy penalty. There's also another problem, and that is the monoethanolamine, or all amines in general, can slip. That is, they can escape from the process into the atmosphere, posing an environmental hazard, as well as an additional cost because that lost MEA needs to be replaced.
The use of solid absorbents such as zeolites, activated carbons, metal organic frameworks are also popular CCS technologies. These solid absorbents have a high capacity for carbon capture and low energy cost for regeneration. However, they lose efficiency when exposed to water vapor, especially in the presence of combustion gases. However, there is still the issue of selective carbon capture in presence of water vapor. The newer technologies in CCS attempt to address problems with current processes. Our current goal is to combine the high affinity of MEA and energy efficient regeneration of a dry system and the low energy cost of solid absorbents, while addressing selective carbon dioxide capture and preserving efficiency even in the presence of water vapor. Fulfilling these goals would make amyloid fibers a very attractive technology in CCS research.
Amyloid fibers are self-assembling protein fibers. Here, these fibers are used as interesting materials for carbon dioxide capture. It's inspired by the use of solid-supported amines, and that CO2 can bind reversibly in bloods by immunogroup in the hemoglobin. The authors are using tripyders of these amyloids, and they have fiber-like morphology, as you can see here in this TEM. We can also look at the chemical structure, which has VQI-VYK sequence. The K peptide here, also known as lysine residues, highlighted here in green, and the amino group of the lysine is what is responsible for carbon dioxide capture. If you look at the crystal structure of these fibers, they have parallel beta sheets, which are held together by hydrogen bonding interactions. The side chains of these peptides have strong steric zipper-like interactions, which make these fibers stable, stiff, and insoluble. If we look at the chemistry happening in these materials, the amino group of the lysine residue reacts with the carbon dioxide and form carbamic acid, which is unstable. Thus, this carbamic acid further reacts with the base, which in this case is the solid buffer salt, and form carbamate. The authors confirmed this chemistry using spectroscopic evidences. So they did cross-polarization carbon-13 NMR and high-power decoupled carbon-13 NMR on these materials, and found there is only one peak present at 163.9 ppm, which is characteristic peak of carbamate. After regeneration of the material at mild temperature, 100 degrees Celsius in nitrogen flow, you can see that the carbamate peak was absent, which basically shows that all the CO2 was released. So these data show here that carbon dioxide reversibly bind on amyloid fiber via carbamate formation. The thermodynamic CO2 absorption capacity was measured by CO2 uptake experiment as a function of pressure. At low pressure, the uptake curves were steep, indicating strong interactions of CO2 with the fibers. At high pressures, the uptake was gradual, indicating the CO2 physisorption. As the pressure was decreased to release CO2, there was hysteresis present, which again indicates the strong binding of CO2 with the fiber materials. This material was then evacuated at room temperature under vacuum, and the CO2 adsorption was measured again. Now we can see that the steep part of the uptake has disappeared, which indicates again the strong binding of CO2 with the fiber materials, and that these room temperature vacuum evacuation was not enough to remove all the CO2. As a negative control experiment, they also measured CO2 absorption on solid buffer components alone, and they saw that there was no CO2 absorption, indicating that all the CO2 was absorbed on the fiber materials itself. And from these measurements, they calculated the thermodynamic CO2 absorption capacity, which came out to be around 0.44 millimoles of CO2 per gram, which is smaller than MEA, which shows around 3 millimoles CO2 per gram. So CO2 absorption capacity can also be calculated using elemental analysis, and they found that 1:1 stoichiometry for CO2 to amine in these fiber materials, which is different than the conventional amine solutions, which shows 1:2 stoichiometry, which is another important aspect of these materials. So in the conventional amines, what happens is when an amine reacts with CO2, it forms carbamic acid, and then this carbamic acid reacts with another amine to form carbamate. That's two amines are used to capture one CO2. They also confirmed this hypothesis by doing experiments in the presence and absence of buffer salts, and it was found that when no buffer salt is present, there was no CO2 absorption, and it was only when the buffer salts were present, which can act as a base, CO2 absorption was observed.
To evaluate the dynamic separation capacity, we used breakthrough experiments to look at the time of appearance or breakthrough of carbon dioxide from the material. The black curve represents solid buffer components, and the red and blue curves represent the fiber materials. As indicated in the graph, fiber materials show much longer retention time for carbon dioxide compared to the solid buffer materials, and this further demonstrates that the majority of carbon dioxide is absorbed by the fiber material. The value is calculated to be around 0.5 millimoles per gram of material. In the graph, solid lines represent carbon dioxide absorption from the dry gas stream, and dotted lines represent gas mixture with moisture. In 3 dry and wet cycles, the breakthrough curves remain unchanged, and this indicates that the amyloid fiber is unaffected by the presence of water. In these experiments, as shown in the inset of the diagram, the experiment setup uses 16% of carbon dioxide in a nitrogen gas stream, and is used to mimic the fraction of carbon dioxide in flue gas from power plants. For the reversal of carbamate reaction of amyloid fiber, heating is always more practical and easier. In this case, when the material is heated to 100 degrees C, the CO2 is fully released and the material is fully regenerated. And the amyloid fiber will retain its morphology through absorption and desorption of carbon dioxide. Besides, amyloid fiber could be engineered, and by increasing the number of amino groups, there is significant increase in binding capacity for carbon dioxide.
Discovery of the applications of designed fiber amyloids in carbon capture was first shown only a few months ago, in January 2014. Therefore, we do not have access to the relevant parameters needed to perform a quantitative economic analysis on these fibers, but the following slides explain the qualitative aspects of their economic, health, environmental, and political considerations. As mentioned before, the regeneration of the fibers only requires heating them up to 100 degrees C, which is much less energy intensive when compared to what MEA would need. However, it's difficult to scale because they're all custom synthesized. They take 7 to 10 days for incubation. However, there's still a potential for more affordable, large-scale production if you were to incorporate bacteria in the production stages. But still, absorption capacity is significantly lower than the leading industry practice, which is MEA. And also, using these fibers are less effective at capturing from post-combustion flue gas, because the post-combustion flue gas conditions of water, acid, and temperature are not desirable for these fibers. Even if you were to capture CO2 from air, the amount of mass flow will have to increase and process becomes much more expensive. One huge advantage these fibers have is that they're biodegradable and non-toxic. If the US were to further optimize their applications in carbon capturing, they will be able to contribute to global carbon dioxide reduction in a very sustainable manner. However, also, these fibers were previously known for the cause of various neurodegenerative diseases such as Parkinson's or Alzheimer's, and which are dependent on their structures. So more research needs to be done to verify whether or not they could be a health hazard.
In conclusion, the use of amyloid fibers in CCS is promising. However, more research needs to be done. We are hopeful it serves as a solution to our current issue of climate change.